All right, so let's get started. So, whoops, if you remember from last time, we were talking about matrix differentials, which are the solution to matrix calculus pain, or at least a partial solution. Your mileage may vary. You can think of them as being either a compact way to write Taylor expansions, or you can think of them through their definition. So the definition is right here. So if you can write the change in f, represented by df, as some function of a and some function a of x, the current point, and dx, the change, plus some residual, which people usually leave implicit. And if this function a happens to be linear in its second argument, right? So a of x comma 3dx is 3a of x dx. And if this residual function here, if this residual r of dx divided by the norm of dx goes to 0 as dx goes to 0, then this expression here is called the differential of f at x. Okay? And this includes sort of the usual definitions of one-dimensional derivatives, but it generalizes a ton of different notions of derivatives that you can see in a bunch of different textbooks. So it generalizes the Jacobian, the Hessian, the gradient, the velocity of a curve, right? And it also includes a whole bunch of things that are really difficult to write in terms of the standard way of writing down gradients. All right? And the derivative is linear, so it passes through addition and through scalar multiplication. And it generalizes, I said that already, it generalizes all of the sort of standard notions. There's a chain rule for differentials, a product rule. We talked about the product rule. It turns out that unlike the scalar case where there's just one idea of multiplication, for vectors and matrices, people have defined many different ideas of multiplication. So there's like the cross product, the Kronecker product, Frobenius product, right? Cauchy-Rao product, and I'm sure somebody tomorrow will come up with a, Frobnitz-Fubbar product that we'll have to learn about. And the product rule is essentially the same for all of them, right? It's the first times the derivative of the second plus the derivative of the first times the second, or the differential. We learned a whole bunch of useful identities, so identities for working with the Hadamard product and with trace. One of the most useful is trace rotation. So if you have something like the trace of A, B, that's equal to the trace of B, A. If A and B are matrices that are such that you can write that and have it make sense. And also we learned about identification theorems. So identification theorems are ways to take the differential, the matrix differential, and read off one of the standard notions of derivatives. And there are 6 different identification theorems for the 6 different types of ordinary derivative that you can express using the matrix differential notation. All right. We went through this kind of quickly, so I wanted to go over it again. If you want to find a maximum or a minimum or a saddle point, right, in one dimension, the standard thing is to set the derivative to 0. And why does that work? Well, suppose that we're here, right, at this point on the curve, and if we look at the Taylor, whoa, that's worse than my usual. If we look at the Taylor expansion, it looks something like that. Good enough. It's a very thick Taylor expansion. And so the slope here is A, right? So if we have this is ax plus b, right? And so if we set dx is equal to some small constant t times a, then the change in x is going to be the change in f is going to wind up being a times the change in x, which is a times ta is equal to ta a squared, right? And so you're going to wind up being able to increase the value of the function by making a small enough change, right? And there are second order terms, but for a small enough change, those second order terms are irrelevant. So if you're, what that means is that if a is non-zero, you're going to wind up being able to increase the function value. So in order for you to be at a maximum, you have to have a is equal to 0. Okay. Now this makes right. If we have a scalar function, there's sort of 3 different types of arguments that we have identification theorems for. So we just did the case of the scalar argument. But if we now go to a vector argument, right? So I've had MATLAB sketch for me an example here. The same thing holds, right? So if we take dx is equal to some small number t times this a vector, right? Then df is going to wind up being approximately equal to t a transpose a, where this is the a vector in both cases, right? And so this will wind up being strictly greater than 0 if a is not equal to 0, right? And so that means that if the slope a is non-zero, you're not at a maximum because you can increase the function a little bit by going in a little bit in the direction of a, right? So now I can just say and so forth, right? So I can't draw pretty pictures when your argument x is a matrix, a tensor, or something weirder, right? But the same principle holds. We can set the coefficient of dx to 0 to ensure that we're at a minimum, a maximum, or a saddle point, right? So if we have, in general, we'll have something like df is some function c of a and dx, where this is linear in the second argument, right? And so if we set dx is equal to t times a, right, we'll get df is equal to c of a and ta, right, which is t times c of a, right? And so we are at a maximum only if this thing is 0, right? Because if this thing is non-zero, then we can pick a small t such that we get a small increase in the function value, right? And so that's a max or a min if and only if we're at a max or a min or a saddle point if and only if c of a and a is equal to 0. Right? And if C is any one of the products we learned about, the Hadamard product, Frobenius, cross product, right, any of them, then that is the same as saying that A itself has to be equal to 0. Right? So we're at a minimum, maximum, or saddle point if and only if the coefficient of dx is 0. Right? All right. So that's the end of the review from last time. Any questions about the review? All right. So at the end of the last time, we started an example which was Infomax independent components analysis, and so I wanted to go through that in now a little bit more detail. So the idea is we have some training examples X, which are in RD. So here's a sketch of some of the X's. And we are thinking of making a transformation. So we set y is equal to g of wx, where w is a tunable parameter, so we want to learn w. And g is a scalar function that we apply component-wise, right? And in particular, we have g takes the real line into the unit interval, 0, 1. Okay? And so if we apply this function component-wise, that means it takes the entire RD into the unit cube in d dimensions, right? And what we want then is to learn w so that the components of y are as close to statistically independent as we can make them, right? Which is a, I'll tell you why that's a useful goal later. But just suppose right now that we want independent components. Well, it's really hard just to say make it independent. So what we're going to do is we're going to shoot for a particular distribution that has independent components, namely the uniform distribution right here, right? So this is an approximation of the uniform distribution on Y. Okay? So that makes sense? Okay. So how are we going to do that? Well, let's take a little detour through the volume rule, which is something that you may have seen in high school or college and may have forgotten since then. So I wanted to mention it again. So if we have some set S, right, and we have a linear transformation A, which takes that to another set S, right? So here I've taken a cube and I've skewed it, rotated it, and gotten another cube-ish thing, parallelepiped, I guess the name is. So if we want, we might know the volume of S, and we want the volume of A of S, right? And so to do that, what we have to do is take essentially the product of its height, width, and depth, right? And it turns out that we can do that by writing the following. The volume of AS is equal to the absolute value of the determinant of A times the volume of S, right? So what that means, if the determinant of A is small, right, that means it has at least one small eigenvalue, which means that A is going to take at least one dimension of the set and squash it flat, right, resulting in a small volume. If the determinant of A is large, that means that every one of the eigenvalues is large, which means that A is going to take our set and stretch it along all of the dimensions, right? So this is the volume rule. Very useful rule, as it turns out, particularly for independent components analysis. So now, what we want to do is do our independent components analysis, right? So we have Y is G of W times Xi, right? And so we know from just the chain rule that we're going to be able to write dyi as some matrix J that's going to depend on Xi and W times dxi, right? And we'll just call that matrix Ji for short. And this is the chain rule plus the identification theorem for derivatives of vector-to-vector functions. Okay? And so what we're going to do is we're going to try and maximize the entropy of Y, right, of the distribution of Y, right, which is max h of p of Y, right? And that's equal to minus the integral of p of Y log p of Y dy. And that's also equal to the minus the expected value of the log of p of Y. Okay? And so we can estimate this expected value here with an empirical sample, right? So it's going to wind up being the sum or the average over a whole bunch of samples I of the estimated log probability at that sample. Okay? And so P of Y, now we get to use the volume rule. Because P of Y is a transformation, because Y is a transformation of X, P of Y is P of X divided by the absolute value of the determinant of the Jacobian of that transformation, right? And so what that means is that if the determinant is small, the Jacobian determinant is small, you're taking a large area in X and squeezing it into a small area of Y, so that small area of Y has high probability, and vice versa. If you spread it out, then it's going to have low probability. Okay? And so we wind up then maximizing with respect to w, the sum over our training examples of the log of the absolute value of the determinant, right? That's here. Right, we cancel that minus sign with the log of 1 over, and then minus the log of p of x. But if you remember, p of x doesn't depend on w, and so we can just drop it and maximize that first term. All right? Yeah?
So y is a scalar here, right?
No, y is a vector, right? So xi is a vector. It's a two-dimensional vector in our example, and we're transforming it to another two-dimensional vector. It's a scalar function which we're applying component-wise, right? So what I'm taking is, let's say, the sigmoid function and applying it to every component of y one at a time. So I'm mapping the entire RD into a d-dimensional unit cube.
So J here also depends on the function g.
That's right. Yeah, I'm taking the function g to be fixed and given, so I didn't write that dependence of j on g, but you're right, j does depend on g. Sorry, there are training examples x1 through xn, each one of which is a vector. So, so this is not the subscript doesn't mean a component, it means our ith training example. Right? So xi is a two-dimensional vector, wxi, since w is a square matrix, that's also a two-dimensional vector, and then g, because it's applied component-wise, it's now still a two-dimensional vector. Okay. Yeah, subscripts are an overloaded notation. I should be more careful about that. Any other questions about the setup so far? All right. So this is just copied from the previous slide. Let's go ahead and do that derivative, right? So what I'm going to do is first do a derivative here of yi. With respect to xi, right? And so by the chain rule, we have dyi, right, is equal to, well, so it's going to be, let's do it component-wise, right? So for each component, it's going to be g prime of the corresponding component of wxi, right? Then times the derivative d of the corresponding component of wxi, right? And because we're doing it component-wise, it's the Hadamard product, right? We take the product on each component, right? And that's equal to then, well, let's see. Let's write then. We'll call ui, so here we'll define ui is equal to g prime of wxi, right? And here then that's ui, Hadamard product then with w times dxi, right? And then if we want to make that into like if we want to get rid of the Hadamard product, well, the Hadamard product is just a diagonal matrix with u on the diagonal times this thing, right? So we'll write this as, well, we'll just write this as diag of ui times w dxi, right? And so now we have an expression for ji, right? So ji is now equal to the diag of ui times w. Okay. So now it's going to wind up being convenient to take the derivative of ui with respect to w. Just saying it's going to be useful later, not justifying why I'm doing it right now, other than we need practice taking matrix differentials. So here again, we can do it component-wise, right? And we can say then that dui is equal to again, if we do it component-wise, we're going to wind up with a Hadamard product. So it'll be G double prime of WXI, Hadamard product with, now it will be dW times XI, right, because I'm taking the differential with respect to W this time. Okay? And so now I will define this here, that I will call VI, right? And so I have VI Hadamard product with dW XI. Okay? And so if I take the differential of the diagonal matrix with UI, with UI on the diagonal, right? Well, that's just then going to be the diagonal matrix with this whole thing on the diagonal, right? So that will be, because diag is a linear function, right? And so it'll be diag of VI Hadamard product with dW times XI. Okay? So now I think we can finally take the differential of the Jacobian, right? And we will get, I'll write that here, dji. I'm going to take that with respect to W. And that is equal to, well, here's our expression for ji, right? And so it's a product, so we're going to use the product rule. So it'll be d diag of ui times W, that's the first part, plus diag of ui dW, right? And now I have an expression for d of, so I'll put parentheses here to show the scope of the d. I have an expression for this, right? That's here, just the diagonal matrix of V times dWxi, right? So this is equal to diag of V Hadamard dWxi times W plus diag of ui times dW. Okay? So this is now we've taken the gradient, right? So if we look here, right? So what we want to do is maximize the sum of the log of the determinant of j of xiw, right? And so now we're finally ready to take the derivative of that function with respect to w, right? The differential with respect to w. And the reason we've done all of this work now, once we get the differential with respect to w, we'll be able to get the gradient and do gradient descent. All right? So now it all makes sense? Okay. So let's finally do that. Yes?
Could you specify again why you were able to change the UI Hadamard product in the second column?
This one right here.
How were you able to justify the becoming a diagonal?
Oh, I see. So UI Hadamard product with a vector, right? So Hadamard product, it's the component-wise product of two vectors. So if I take a vector and I multiply it by a diagonal matrix, well, then I'm going to multiply the first element of the vector by the first diagonal element of the matrix, second element by the second element, right? So it's just another way to write the same Hadamard product. Right, right. So if a Hadamard product of two vectors, I take one of them, I put them on a diagonal matrix, it becomes ordinary matrix multiplication. Okay. All right. So So this stuff here is all just copied from the previous slide, right? Our Jacobian is diag of ui times w, and the differential of the Jacobian is diag of ui dw plus diag vi diag dw xi times w, right? Just make sure that that is, in fact, what we wrote on the previous slide. Oh, it should have been, yeah. Here we go. So I wrote it in the opposite order here, but it is in fact the same thing. Okay, so now dl, right? So if L is the thing we're trying to minimize, dl is then the sum over training examples I of the differential of the log absolute value of the determinant of ji, right? And we know one of the one of the identities that we talked about before last time lets us take the differential of log det, right? So this is going to be the sum over I of the trace of ji inverse times the differential of ji. Okay? And now we have ji, and we have the differential of ji, so we can write that out. That's equal to the sum over I of, okay, so now ji inverse times this first term, right? So we're going to get w inverse times diag of ui inverse, right? When we invert them, they swap orders. That diag of ui will cancel this diag of ui, right? And so we will then get w inverse dw, right? So that's the first part. Oh, I forgot the trace out here. Trace. And then the second one, we're going to have plus w inverse diag of ui inverse diag of vi diag of dw xi times w, right? I copied all of that out, right? Okay, so now I can use trace rotation to move this w inverse over to this end, right? So this just cancels with that. So that's nice. I'm going to define a new notation to save myself a little bit of writing. So I will call this whole thing, this part here, this will be diag of wi, right? So v over u is w. And so now I have this is equal to the sum over I of the trace of w inverse dw plus the diag of wi times diag of d capital W xi. Okay? Sure. Pick a letter that I'm not using. How about alpha? I don't think I'm using an alpha anywhere. So let's call this one alpha I. Right? And this is now alpha I. Sound good? That's an excellent point. Notation is complicated enough to start out with. Okay, so now I'm just going to break this up into two terms, right? So I can write this trace plus trace of that, right? And now the trace of a product of diagonal matrices, that's actually just the ordinary dot product between those two vectors. And so we now have that this is alpha I transpose dw xi. Okay? And so this whole thing then becomes n times w inverse dw, because it doesn't depend on I at all, plus the, going to move the sum inside the trace. So this is now a trace of alpha, the trace of the sum over I of alpha I so I'm also going to do one more thing, right? So I have the trace of this thing, and I can use trace rotation to bring the x to the front, right? So I will get trace of the sum over I of xi alpha I transpose, right? That whole thing times dw. Okay? Yeah. I'm sorry? You're right. There should be a trace on the first term. Okay, and now I can use the identification rule to read off the actual gradient, right? So the gradient is the transpose of the coefficient of dw, right? So it's going to wind up being well, so let's write it out. So we'll have dl by dw is equal to w inverse transpose plus n times w inverse transpose plus the sum over I of x, well, the transpose of this thing, right? So that's going to be alpha I times xi transpose. Okay. This is the identification rule, right? So if you have the differential of a scalar function of a matrix argument, the identification rule will let you get the actual gradient, which is the transpose of the coefficient of dw. Okay? All right. And so just for notation, I will say that this will be n times w inverse transpose plus c, where, so this is a notation, defined equals. C is now 1 over n times the empirical covariance between alpha and x. Right? Okay, so this is a nice, simple expression for the gradient that we got after, well, a ton of matrix calculus. But everything, cancels out, and in the end, it becomes pretty. And this would have been actually a lot worse if we were trying to do this without the matrix differential. So, you can be thankful that it wasn't worse. And now we can do gradient descent, right? So we have this gradient. We can update W by figuring out W inverse transpose plus the covariance of alpha I and xi, right? And alpha I we can compute from xi and our current parameter values. Okay? So that's kind of cool. It turns out that what people actually do is something even more clever. They use what's called the natural gradient. So there's a lot of theory that goes into defining what the natural gradient, why you would be interested. But it turns out that the actual definition is kind of simple. So here it is. We have a scalar function of a matrix argument W. And we've written the differential as the trace of some matrix G transpose times dW, right? And G here could be a function of W, but to make the notation simpler, I'm just keeping it G. And what we're going to do is we're going to do steepest descent, but with an adaptive norm. So we're going to use a different norm that depends on the current value of W. So what we're going to do is our step is going to be the argmax over S of some function m of S, which is the dot product between G and our step, right? Minus the size of our step measured in this adaptive norm. And the adaptive norm is the squared Frobenius norm of S times W inverse, right? So why would we pick that, right? What is that doing? Well, if you look at the scalar case is G times S minus S squared over 2W squared, right? So if W is really, really small, what that means is that the quadratic term has a really large weight and will make really small steps, right? And if W is really, really big, the quadratic term is going to have a tiny weight and will make really big steps. And so what this is doing, it's taking an adaptive step size so that you're making smaller steps when W is closer to the origin and larger steps when W is farther away from the origin. And with a matrix, you're doing something similar. You're making smaller steps when W is close to being singular and larger steps when W is very well conditioned, far away from being singular. Okay? So it sort of makes sense, especially if you have an update rule that involves the inverse of your matrix, as we do, that you would use this sort of adaptive steepest descent, because you're trying to sort of avoid your derivative is going to be changing a lot as you move around close to singular matrices, and so you want to be very cautious. Okay, so I can just rewrite M as the trace of G transpose S minus the 1/2 the trace of, and now here I'll just write this out as S times W inverse times W inverse transpose times S transpose, right? That's another way of writing out the Frobenius norm. And so dm is going to be simple to get. It's going to be trace of G transpose ds minus the trace of, and now here there are two different copies of S, and so we're going to use the product rule will mean we'll get this term twice. Once will be transposed, but since we're taking the trace, it doesn't matter. And so we'll get 2 times the trace of ds W inverse transpose S transpose. Right? And now I can use trace rotation to move ds over here, and then I get the coefficient of ds, right? The transpose of that is the actual gradient, so I get the gradient being G minus W inverse, sorry, the whole thing is transposed, so it's going to be S times W inverse transpose, right? And I can set that equal to 0, which means I set G equal to that thing. Multiply through by W and W transpose, and I wind up getting G times W transpose W is our step. Okay? So all of that math goes through to say that we just take our gradient and we multiply it by W transpose W, and we get the natural gradient, right? And natural here is with respect to the geometry of the set of matrices, where matrices are changing faster when they're near being singular. Okay? Yeah? This term here, trace of G transpose S. Right. So in steepest descent, what we want to do is we want to maximize a quadratic approximation to our objective function, right? So this is the dot product between the gradient and the step we're taking. So that's the linear part. And then the quadratic part is the squared norm. And we get to choose the norm for different steepest descent. Okay? Okay, so we wind up taking the gradient and multiplying it by W transpose W, which is kind of cool for us because we had a gradient with an inverse in it. And what that means is when we multiply by W transpose W, we get just W plus C W transpose W, right? And our inverse disappeared. So this is good for two reasons, right? The first reason is just that it's cheaper. We don't have to compute a matrix inverse in order to get our gradient. And the second is that it actually converges faster because we're paying attention to the geometry of the set of matrices. So when people thought of this, they jumped on it, right? When somebody first thought of this, everybody jumped on it because it converges a pretty big factor, fewer iterations, and each iteration is much cheaper. And in fact, you can even use a stochastic natural gradient, in which case you wind up getting a very cheap estimate of the gradient and multiplying it by W transpose W. And there the expense of the matrix inverse is even worse, right? It's even worse to have to compute a matrix inverse every time if it's really, really cheap to get the gradient. And so stochastic natural gradient winds up being a huge win for this particular optimization, and it made it really practical for the first time. Okay? So that's kind of cool. And let's actually just show you what this looks like. So here I have, this is W times xi right here, right? And I started with W equal to the identity, so this is actually also just xi right here. And this is yi, which is g of W xi. Right? And what I'm going to show is an animation that shows how this changes as we make the natural gradient updates. And so it looks like this. Right? And you can see that quite rapidly it goes and makes it so that W times xi has approximately made the axes orthogonal, right? The main axes, and so it's statistically pretty close to independent. And it's made this cloud pretty close to uniform when it started off pretty far from uniform. Okay? So that is the natural gradient, and that is ICA. And what people actually do with this is, for example, you can do it on patches of natural images, right? So what that means is you take a photo such as this beautiful photo from out in the Laurel Highlands. You take small square patches of the photo, right? So you dice it up. You take, here we have just 5, but you take, thousands from each image. Each of those is going to be, let's say it's a 12 by 12 patch. It'll be 144 numbers. So you treat it as a vector of length 144. And you do independent component analysis on that sample of length 144 vectors. Okay? And so what that does, if you do it on natural images, so here these are the result of ICA on some 12 by 12 grayscale patches. So we learned a matrix that's 144 by 144. We take a particular row of W, right? So that's something that we take the dot product with our image patch. We think of that as itself an image, right? So it's a filter. We take the dot product of that of the image of coefficients with the image of actual image, right? And so what I've done is I've taken 84 of the 144 rows of W, and I've reshaped them all into images and plotted them. And you can see that what happens is that you get, these are essentially oriented edge filters, right, of different scales and different orientations and locations, right? And so you have some, for example, this one here, right, this is a, this is a big edge, right, something like that, right? We have, we have sort of medium-sized edges, right? Here's a sort of medium-sized edge at a different orientation, and we have little edges, right? So here's a little edge there, right? So this is what primary visual cortex does in, well, basically all primates and a bunch of other animals as well. And so it's really kind of cool right? This algorithm didn't know that you were giving it image patches at all, and yet when you asked it for sort of the optimal statistical description of this in terms of the independent causes, it does exactly what primary visual cortex is doing, right? So this is maybe an explanation for why primary visual cortex is doing what it does. It's trying to extract the independent causes of sort of small patches of the image that you're looking at. All right? So that's kind of cool. All right, so that's matrix differentials. There's a ton more information if you want to study, so I just wanted to point out this cheat sheet is really, really useful. It's very, very dense, so I wouldn't have recommended trying to read it before we spent a lecture and a half talking about these things. But now that you've had that, I think you'll be able to read this and get a lot out of it. It's a great reference for learning about this. And then all of the gory details are in Magnus and Neudecker. This is a 300-something page book that goes and proves when these differentials exist and when they're equal to the ordinary notion of derivative. So if I wouldn't necessarily recommend reading through it cover to cover, but if there's some point that you're confused about, there will be a nice detailed explanation in Magnus and Neudecker. And then finally, the ICA stuff. The results I stole from Bell and Sejnowski's paper. They were one of the ones who first proposed this in neural computation in '95. All right. So any further questions about matrix differentials or the examples? All right. So now we get to Newton's method. And I think that perhaps it would be a good time now to take a brief break, so we'll break for a couple of minutes, and when we come back, we'll talk Newton's method. All right, so let's get back started again. So Newton's method, right? So you guys have been doing first-order methods now for about not quite a dozen lectures. So now we're getting to second-order methods. Should be very exciting. Okay. Suppose that I want to solve a set of nonlinear equations, right? So here a set is just one, but in general we could have some variable x which is in Rd and some function that's differentiable from Rd to Rd, and we want to solve the set of nonlinear equations that's just f of x is equal to 0, right? And so, for example, if I wanted to find, if I had some real number like the golden ratio, 1.618 something, right? And I wanted to find its reciprocal, right? I could take my function x to be 1 over x minus phi, right? So here's a plot of that. And the 0 of this function is where 1 over x equals phi, so it's where x is equal to the reciprocal of the golden ratio, right? So that's a nice nonlinear function, and I can try and find a 0 of it. So I can Taylor expand f, right? And so I can say that f of y is approximately equal to f of x plus the Jacobian j of x times y minus x, and that I'm just going to define to be equal to f hat of y, right? And j of x is the Jacobian at x, right? And so what Newton's method is going to do is, instead of solving f equals 0, which is hard, it's going to solve f hat equals 0, which is easier, right? F hat of y equals 0. And of course, since we solved an approximation to the equations, we don't get an actual solution, but we might get closer to the solution where we can make a new Taylor expansion and repeat the process, right? So if we start here at x equals 1, right, that's here, and draw the Taylor approximation, right, that's going to wind up being 1 over 1 minus phi, right, so that's 1 minus phi plus the derivative. Well, so this is f is that, right? So f prime is equal to minus 1 over x squared, right? And so if I evaluate this at x equals 1, I get just minus 1, right, times dx times, right, y minus x. Okay? And so if I solve this for my new y and set it equal to 0, right, I'll get over here, which if you ask MATLAB, it turns out to be about 0.318. Right? So that's Newton's method. So in the general case, Newton's method is we say that f of x plus j of x times y minus x equals 0, right? And so we get that y minus x is equal to minus j of x inverse times f of x, right? And so this inverse is the source of basically all of the problems with Newton's method. But if you can live past those problems, you get a lot of benefits. So for example, problems include the fact that j could be not invertible, right? Or j could be really big, right? In which case you pay d cubed for the naive way of solving this set of equations. So, all right, so that's Newton's method. And we can analyze the error in Newton's method for this particular case pretty easily, right? So if we define, well, that's interesting. For some reason, there we go. Okay, so apparently I still don't quite know how to use my tablet yet. But if we define our error to be epsilon is equal to x times phi minus 1, right? So if that's the case, all right, so this is 0 if x is in fact the exact reciprocal of phi, and it's not 0 otherwise. And if we remember that our Newton update was that x plus is equal to x plus x times 1 minus, so I didn't actually derive that. So let's go back a page and derive that. So here, right, in our example, we have that f hat is equal to f of x minus 1 over x squared times dx, right? And so the step is going to be that when we set that to 0, right, it will be this is here f of x is 1 over x, right? And so if we set that equal to 0, we can 1 over x minus phi, right? And if we set that equal to 0, we can multiply through by x and say that 1 minus x phi minus 1 over x dx is equal to 0. Or if we multiply through by x squared, we can get x minus x squared phi is equal to dx, right? So dx is x minus x phi, is x times 1 minus x phi, right? So now x times 1 minus x phi is our step, right? And we add that to x to get x plus. And so epsilon plus, right, the error at the next step is equal to x plus times phi minus 1, right? And so that's equal to, well, x plus x times 1 minus x phi times phi minus 1, right? So this here, right, that is minus epsilon, right? And now if I multiply this out, I can get x phi minus x epsilon phi minus 1, right? X phi minus 1, right? That's another minus epsilon minus, sorry. Yeah. What's that? This is, yeah, this is plus epsilon minus x epsilon phi, right? We factor out the epsilon, epsilon times 1 minus x phi is equal to minus epsilon squared, right? So that's interesting, right? Because it means that if we do one iteration of Newton, we wind up squaring the error, which if the error is bigger than 1 is a bad thing. But if the error is smaller than 1, it makes it smaller really, really fast, right? So for example, if epsilon is a quarter, 2 to the minus 2, then you square it, it'll be 2 to the minus 4, and you'll flip the sign, right? And it'll be 2 to the minus 2, 4, 8, 16, 32, right? So it goes down to 0 really fast. And it takes, if you look at it, it takes 5 steps to get to 2 to the minus 64, which is more precision than there is in an IEEE double, right? So 5 steps of Newton's method will suffice here if we initialize within a quarter. And so if we initialize at, so we know that phi is between 1 and 2, so we know 1 over phi is between 1/2 and 1. So if we initialize at 0.75, we have error of no more than a quarter, right? And so I've just written here the steps of Newton's method, and I've put in green the digits that are correct, right? And so you can see it's going like, you know, less than 1, 1, 2, 5, 10, 16, right? Actually, perhaps more than 16, but we can't see it, right? So here we're getting this last digit is going back and forth because I'm showing 16 digits, which is just at the limit of double precision. But really, really fast, we get more and more correct digits, okay? And it turns out that this is actually a practical algorithm for division. Some processors use this. If you have an arithmetic unit that can do a fused multiply add, you need 2 fused multiply adds per iteration. And so you need no more than 10 multiply adds every time you want the inverse, right? And so since fused multiply adds can be pretty fast, this is a pretty fast way to get divisions. Okay. And it works because it happens that the Newton step has no divisions in it, right? It could have turned out that the Newton step had some divisions in it, in which case we wouldn't be able to use this as a division algorithm. But because it didn't, then we're good. Okay? So if we have a bad initialization, it looks like that, right? That's not what we want. And that sort of brings home the point that Newton is only a locally convergent algorithm, right? So if you initialize close enough to a solution of your nonlinear equations, then you're good. if you initialize far away from that solution, you could go off very, very quickly into no man's land. Okay. So now, from the point of view of this class, we want to use Newton's method not to solve sets of nonlinear equations, but to optimize something. So now we have some variable x that we're optimizing over and a function f that we want to minimize, right? So we're finding the min over x of f of x, right? And that's f is a function from Rd into R, and we'll assume that it's twice differentiable. So in order to find the minimum, we're going to set its derivative to 0, right? So we say 0 is equal to f prime of x. And to save me writing primes, I'll write that to be, I'll just define f prime equal to g of x, g for gradient. Okay? And now g is going to be a function from Rd to Rd, right? And so now Newton's method for solving g equals to 0, well, it just says that the change in x is equal to minus g prime of x, which is a matrix, invert that, times g of x. Or if we write it in terms of f, this is minus f double prime of x, inverse times f of f prime of x, right? And so that's equal then to minus the Hessian of f inverse times the gradient of f, right? And this is the form maybe that's most familiar for Newton's method, minus the Hessian inverse times the gradient, right? So again, it's got the same benefits and problems as regular Newton's method. It's extremely quickly convergent. It's quadratically convergent. It's only locally convergent, so you have to initialize near the minimum or hope that your function is really, really nice. And we have to solve a d by d system of linear equations every iteration. So if d is 1,000,000 and your Hessian is dense, then you're out of luck. Okay. But you inherit some actual additional benefits from using Newton's for a minimization problem, right? So here's the Newton step again. D is minus the Hessian inverse times the gradient. The gradient step is just the negative of the gradient, right? And so if we make a Taylor approximation of f, right, df is approximately the gradient transpose times dx, right? And then I'm going to explicitly write the residual of dx here, right? And suppose that we set dx is equal to t times the Newton direction, right? So we do a small step in the Newton direction. Then we get that df is equal to, so df is equal to the gradient, right? So that's f prime of x times d, right, which is minus t times f double prime of x inverse f prime of x, right, plus then the residual of t d, right? And so if t is small, right, and if this thing here is positive, then I can get a decrease, right? This will be negligible for small t, and this will be strictly negative if this thing in here is positive, right? And when is this thing positive? This is positive exactly if, right? This is greater than 0, exactly if f double prime of x is, as a matrix, actually strictly positive definite, right? So when is that convex? Well, we looked at that before, right? That's the second order convexity condition. Sorry, when is that positive definite? Exactly when it's strictly convex, right? So the Newton direction is actually a descent method, right? Newton's method is actually a descent method for minimizing a strictly convex differentiable function. right? And because it's a descent method, that gives us some more options, which we'll get into in a couple of slides. And in fact, it's an example of a descent method that we've seen before. It's an adaptive steepest descent method, right? So this picture is shamelessly stolen from the textbook. If you have some point x here, right, and you compute its gradient and Hessian, so here's the gradient, right? This is just a vector going off this way. And you define a norm, which we'll call the Hessian norm. And you define the Hessian norm to be the square root of d transpose h d, right? Then, the steepest descent method in this norm says that what we're trying to do is to minimize over our step direction d of the gradient transpose times d plus the Hessian norm of d squared, right? And this part is just d transpose h d, right? And if you solve this, you'll get exactly that d is equal to minus h inverse g, right? And so you'll get the Newton step here to x plus the Newton step. Okay, yeah? Right. If it's strictly convex, then its Hessian is invertible always, and so you'll never run into the lack of an inverse. Of course, you will still have the problem that you're inverting a d by d matrix, right? But you can still get bad initializations for Newton with strictly convex functions, but that's actually a great segue, thank you, into the next slide. Since it's a steepest descent method, that means that you can do line search, right? So you know that the function's actually getting smaller in that direction, and so you just you can, if your step is too far, you can take a smaller step and be guaranteed that the function is always going down, right? So this is what we'd actually use, Newton with line search, also called damped Newton. You start with an initial guess, which can be then anywhere in the domain. And then you, for iterations k, 1, 2, and so forth, you compute the gradient and the Hessian. You get the Newton direction as minus the inverse of the Hessian times the gradient, right, which you never write by computing the inverse. You always do it by solving a system of linear equations, which I've got. This is the MATLAB notation for that. You start off with a full Newton step, t is equal to 1. And while you don't have sufficient decrease, this is the same sufficient decrease condition that we saw with line search for gradient descent. You set t to be beta times t for some beta that's less than 1, right? And so you're going to guarantee here, if you remember, we had a picture like this, where we have, here's the approximation, right? Right, so that's at this point. And if we go with half of that slope, right? So if we take a full Newton step, let's say that's out here, that doesn't get us as much decrease as if we had had half the slope. But if we, let's say, divide that by 2, we'll get to here. And with t equals a half, we will get sufficient decrease, right? And then once we've figured out a step size t that gets a sufficient decrease, we just take that step and we repeat. All right? So that's the Newton method with line search, and that works because we've proven that Newton's method is a steepest descent method for strictly convex functions. Okay? Now, one thing I want to point out is that this here, right, this is the predicted amount of decrease that you would get if you took a step size of 1. That's also called the Newton decrement, right? The expected amount of decrease that you would get if you took the full Newton step and everything were nice. Okay. So just briefly, the properties of this damped Newton algorithm. It's affine invariant. I'm not going to prove that, but you can convince yourself. What that means is if I have some function f and I define g to be f of ax plus b for a matrix A and vector b, and if I take x1, x2, and so forth as Newton steps on g, and y1, y2, and so forth as Newton steps on f, then if I initialize them at corresponding places, y equals a times x1 plus b, then we'll actually have that yi is equal to a times xi plus b for all I, right? So we're doing essentially the same thing, right? Newton essentially ignores an affine change in the function. It's also convergent. So the fact that it's a descent method means that if the function value is bounded below, then the function value has to converge, right? It's a decreasing sequence bounded below, and so it has to have a limit. You can also prove, I'm not going to do it, but it's a relatively simple argument, that if your function is strictly convex and its level sets are bounded, then the actual iterates converge, right? So we know that the function values converge, but if it were like, let's say, 1 over x and you were minimizing it, right, you could have the iterates themselves go off to infinity. But if it's strictly convex with bounded level sets, the iterates themselves are actually going to converge. And it typically has a quadratic rate in the neighborhood of the optimum. Okay. So I think this might be a good place to stop, and we will continue with Newton's method next time around.